It's my pleasure to introduce our next speaker, Tyler Johnson. Tyler did his undergraduate studies at Rice University, where I was at the same time that he was graduating. And then he went to UIUC to do his PhD. And since then, he's been working on the verification of cyber-physical systems using a variety of techniques, especially reachability analysis. And now he's an assistant professor at Vanderbilt University. So without further ado, welcome, Tyler.
All right. Thank you, Waleed. Thanks, everyone, for being here, too. I'm a little jet-lagged because my anticipated 12-hour trip turned into about 26 hours. So if I say anything crazy, feel free to stop me. And I'll blame it on that, of course. Just get coffee ready, because I will surely need that. Okay, so did I turn the mic on okay? Good? Okay, all right, perfect. So I'm going to give somewhat of a high-level introduction today, but a couple pieces of things that we'll need. So kind of a broad overview of formal methods within cyber-physical systems, in particular models of systems such as hybrid automata. Then the later lectures I'll talk in some more detail about how we can model machine learning components in autonomous CPS and how we can verify them using some recent techniques. And I'll give a little bit of an overview of that. And then the last part I'll talk about in the third lecture will be in doing runtime verification, where we'll monitor these systems at runtime as trying to do formal verification for things like neural networks is going to be very challenging for the size of networks that show up in these types of systems. So of course, feel free to stop me at any point. So we work within CPS, so I think everyone is fairly clear on what these are. We have physical plants, environments, maybe humans, controlled or interacting with some software, possibly over a communication network and with sensors and actuators. Lots of application areas, I'll talk about a few of them, but things from medical devices to transportation, as we heard about earlier today, encompassing in things like the smart grid and Internet of Things. So I'm going to present a little bit of information on why even non-autonomous CPS are very difficult to design. And you can look at it a few ways. So I'm a little pessimistic on things like autonomous vehicles getting here in the time frames that the media and others may have us believe. So I'll present some data on that. Obviously, and eventually there are some major benefits systems like that could provide, but I'm going to argue we can't even build non-autonomous cars correctly. So that will be my argument, basically. So within our work, typically we're focusing on distributed CPS. So I have a couple video demos. Anyone heard of this Perdix demo? Nobody? Okay. So I'm going to fast forward a little bit because the video is a few minutes, but this is a pretty cool system. So what's happening, these aircraft are about to release a swarm of drones. So the date of this was in 2016. So you can imagine they're very tiny. They're dropping out of these pods. But I'm going to fast forward to an overhead view. So that's when the vehicles are deployed. And this is sped up a bit. So after they're released from those fighter jets, then they're going to be given some different commands. So go to these waypoints. There's about 100 of these small drones in total. Go to some waypoints and they're going to perform some other fairly simple missions, but good for demonstrating this type of a system. So a lot of communication going on, obviously collision avoidance. So I find this to be a nice example of a cyber-physical system, a lot of real-time constraints, a lot of pieces going on to make this work appropriately. Some human-computer, human-robot interfacing, the operator who would be controlling this and providing these sets of waypoints and commands that need to be distributed appropriately amongst all these agents. So forming kind of a semicircle around a target, say swarming a target, maybe kamikazeing into it or something, orbiting around a common point. So kind of a cool demo. So then I saw this one in the last couple weeks out of China, which is a distributed swarm of boats. Anybody happen to see this one? This came out in the last 2-3 weeks. But similar thing for boats. So you can imagine other scenarios where these types of systems are showing up. And then finally, maybe just one more fun introductory video of a kind of autonomous intersection. Anyone seen this video? No. Okay. All right. So maybe the future if we get there. So since most of you have seen it, we'll keep going on. So those things may be enabled. All these examples, and just to illustrate it for vehicles, a little bit more of what all would be going on. So this would apply in that swarm system as well, obviously with some wireless interfaces. Within vehicles, as we start to move towards increased communication, such as through vehicle to infrastructure, networking in these vehicles, which can provide a lot of benefits similar to what autonomy could provide, but even some potential to do some things autonomy can't provide. So knowing state farther ahead down the road, for example, which you wouldn't be able to necessarily sense from one vehicle. You really need a set of vehicles to do these things. But all of these are networked, in many cases, internet-connected systems interacting with the physical world, in this case, a computer on wheels. So a lot of internal networks within a vehicle. Then as you start to, say, hook up your Android Auto device or whatever, Apple's CarPlay or whatever these things are, there are interfaces from your smartphone, and obviously it's internet connected to the vehicle. You might think that there's a separation between that type of infotainment network and the internal network of vehicles, although in many cases that's been demonstrated to be false. So being able to attack a vehicle through your phone is possible, as are if you can get access to some of these internal networks. So security is something I'm going to talk a little bit about down the road, but something I wanted to mention is another motivation. So broadly what we work on is verification. So this verification challenge, we call it a challenge because it dominates what we actually do in engineering and computer science in terms of resources. So we have some system model and some specification. We'd like to come up with a method, if it's possible, to do that, that would, provided that system model and a spec, either say that yes, the system satisfies the specification, or if not, come up with a counterexample as to why it does not. So across engineering, this dominates cost. So in a company like Google, which in general is not making safety critical systems, sure, they might lose money if their system goes down, but the typical figure you'd hear is for every one software engineer or software designer, you'll have one software tester. So about 50% of effort or cost is on V&V, verification and validation. In a domain like aerospace, where there are very stringent certification requirements, the figure would typically be for every $1 spent on design, you're going to spend $8 to $9 on V&V. So maybe upwards of close to 90% of effort is spent in this process. So trying to make sure systems do what they're supposed to do. This, I don't know of a more recent study than this, but we can certainly imagine this figure is a whole lot higher now. So that was a Hist study that quantified the economic cost on the US economy of software bugs. So obviously there's a lot more software today than there was in 2002. And then as being in academia, there's some interesting theoretical reasons for the types of models that we look at. Oftentimes this problem is undecidable, so we can't come up with an algorithm, but we may be able to come up with a semi-algorithm. So if something terminates, then it may have solved this problem. And then other challenges are state space explosion. So roughly speaking, this problem gets exponentially more difficult in the size of the system. And we'll see in a second that the size of the systems we're building is also increasing exponentially. So that means we have a doubly exponential growth in the sort of practical challenge of this problem, because our systems are just getting so much more complicated. So our models will be network software interacting with the physical world. So in our case, we're going to talk about hybrid automata. I'll talk some about learning-enabled components as well, particularly neural networks. And then what the types of specifications we'd have typically would be safety, which is primarily what we'll talk about, or possibly stability in a control theoretic or in a computer science perspective is something like liveness. So get to some good states eventually and remain there. And safety, an example, for instance, in the Perdix swarm would be, say, that the drones aren't colliding. Although maybe if there's so many, we don't really care too much if they do. So our systems are getting a lot more complicated. So these are just a couple figures. This is a bit better way to look at it. That backs up the point that I made, that the systems we're building are getting exponentially more complex. So this is measured in this case in terms of source lines of code. That's not a perfect measure of complexity of a system, but it's some measure. And I think we could argue having more code is probably a bit more complex. So this is in DoD systems, upwards of 24 million-ish lines of code in the F-35, so it's getting to be quite complicated. So we can see that these types of systems, in this case, all of which are non-autonomous, are getting more complicated. As we start to throw in autonomy, we're going to have an additional growth in complexity. All right, so let's back up just 1 second, and I want to ask you all a question. So who believes autonomous vehicles today are safer than human drivers? Anyone? No one. We're all pessimists in the room. Okay. All right. So sometimes we're all technically minded, so we may know something about what goes on. Maybe recent media reports influence some of this. But I'll just give you a little bit of data to back up the claim that autonomous vehicles as are being tested on the road today are 1 to 2 orders of magnitude less safe than human drivers. So they're that much worse. So the data that backs this up is the standard metric. One of the standard metrics that's used for this would be fatalities per mile driven, or the inverse of that. So in the US, we drive about 3 trillion miles a year, a bit over that, which amazingly is about half a light year. Think about that for a minute. It's quite a lot of driving. So there's about 37,000 fatalities. So if you divide this out, we have 1 fatality in the US per about 85 million miles driven. So autonomous vehicles in total across all the manufacturers have driven on the order of 10 million miles in ideal conditions. And there's at least 1 fatality, certainly, but probably more. So on the order of 1 to 10 fatalities. So depending which number you pick there, that's 1 fatality, 1 to 10 fatalities per 10 million miles driven. So that's 1 to 2 orders of magnitude less safe than what humans do. Comments, questions? Anyone want to disagree with any of that? All right, okay. Well, y'all were easy to convince. So now I'm just going to give a little bit of motivation on why I would argue that non-autonomous vehicles we can't even design quite correctly, right? There are a lot of bugs and things. So security is becoming increasingly important. Probably most of you have seen this now old attack, which was an over-the-air attack that did not require any physical access to the vehicle. So if you could find out the IP address on the internet of this Jeep vehicle, you could attack it and get control of interfaces connected to the CAN network. So purely over the internet, no physical access required. Obviously, you need to find that address of this vehicle, though. And more recently, there have been a bunch of other instances. So if you look outside of these types of domains, this also occurs even in heavily certified systems. so in aerospace. In automotive, we have recalls, typically in the US by the NHTSA or NHTSA. There's similar organizations in other countries that are regulating and keeping track of things like safety defects. Aerospace is a little harder to find. They're not called recalls, they're called airworthiness directives. So at any rate, this is an instance of that due to a timing error where you could lose functionality of spoilers, so some control surface of the plane, which would result in decreased controllability of the plane. So not that long ago, so some other autonomous vehicle instances. I'm going to go through these quickly because I think I don't have to convince you all too much, it seems. So this was a neat instance, though, that happened with Toyotas. So it happened 2 years in a row. They didn't quite fix it. So there's a converter in the hybrid drivetrain that steps up voltages that you'd be getting from the battery to actually control the motor in the hybrid drivetrain. And as a part of that, there are power transistors that are used in that process. So this boost converter circuit has these IGBT power transistors, and in this scenario what could happen is that control software for these motors could put those transistors into a thermal runaway mode. The packaging on them would melt, and then you could lead to shorts and stalls. So I think this is sort of an interesting cyber physical defect example. So if we look at aggregate data, this is from a paper we presented at a NHTSA conference a couple years back. In ISO 262 lingo, what we're looking at here are electrical and electronics defects measured by recalls or notifications. In this case from Transport Canada, which is like NHTSA in Canada. And what we're trying to quantify here is what percentage of motor vehicle recalls are due to, in essence, software issues, right? So how many software issues are there? Is it growing? So as a percentage from this chart, it's a little difficult to see. From this one, it's a little bit easier to see. But these recalls are increasing, right? Which makes sense. It's just part of how these systems are designed today. Everything is drive-by-wire in a modern vehicle, whereas used to be there would have been other mechanisms by which different components in a vehicle would be controlled. So since we're a little bit introductory, what's happening here? So this is about 2015, which is when we stopped this data collection. Are we just sort of all of a sudden a lot better? Hazard a guess. Too early in the morning. Okay, right, so if we kept projecting out what this trend line would look like, what's happening here, we don't immediately find all the defects, right? It takes time after we have some problem in the deployed system for people to complain about it, for accidents to occur. So we may be getting a bit better, or there are actually the real data for this would roughly follow this trend line and continue increasing. And these would just represent defects that haven't been found in deployed systems. Right, so that's a little bit concerning, but in this paper we also did some analysis of how long does it take for a defect to be found. And there's some differences between software and mechanical components. All right, so I'm going to keep going so we can get on through a few things. I'm happy to share all these. So those are a few examples. I listed some from aerospace and automotive. You can look in basically every domain. Elevators, fire alarm control systems. What's interesting, what are the manufacturers? In this case, Bosch, Tyco, and Simplex Grinnell, Honeywell. All these things happen across all manufacturers. So it's not like everyone's just not doing a good job. It's just really hard. So obviously, if there's a fire, you probably want your fire alarm system to tell you, particularly in a building like this. where we may have to go down 20 flights of stairs. So even other random things like scuba diving computers and not correctly displaying tank pressure, which would be bad. Medical devices, similar story. So this FDA report indicates that software defects are now tied with manufacturing defects as the #1 reason of medical device recalls, which is a little bit troubling on its own, but it's even more troubling when you think and say, well, not all medical devices have software in them, do they? Right, whereas basically all medical devices are going to have some physical component. There are some software-only medical devices. All right, so that's probably enough motivation, but some data indicating we have problems even with traditional CPS in getting things right. So what do we do about that? So broadly, our group's research is at the intersection of formal methods, which historically maybe would be in theory, but these days I think is more reasonable to put in software engineering, maybe systems engineering if we're in CPS, and then hybrid and distributed systems, and then in a variety of application areas. So I'll talk a little bit about some robotics, aerospace ones. So these are some CPS that we have in our lab, just groups of robots. Nothing too fancy, but some test beds that we have that are similar in some sense to things like the Perdix drones. So we use these for evaluations. Some of these things will come up later on. So we do implement distributed algorithms in these things, and you have all the concurrency types of primitives that you would need, things like leader election, mutexes, clock sync, all sorts of things. So there's a lot of distributed aspect of this. All right. Okay, so let's get back to our intro and talk a little bit more in depth about this particular problem. Any questions before digging into some of this? Good, all right. So we have a system model and a specification. We'd like to prove that the system model satisfies that. So you can think of this in a few different ways. So by proof, I do mean proof in a mathematical sense. But if you want to think about this in a more practical engineering sense, this would be provide evidence, right? So there are a few veins in which we can think of this, but the perspective to keep in mind now is that we do want a proof of this, so a guarantee. But there's some more practical aspects that could be considered without that mathematical, somewhat academic, philosophical perspective. A lot of potential issues with this when you talk about robustness of the models and whether they actually are valid models of the physical world. For software, it totally makes sense, and for digital logic, but for CPS, I think there's some questions on whether we can actually get proof. So what are the system models? What are the specs? So I'm not going to drill down into all of the details of that, but I'm going to talk just briefly about the syntax and semantics of models and specs, primarily through pictures. And then what does this mean? So how can we prove this? So I'll talk about how we can do that with reachability. All right, so I'll start with one of our canonical examples. So I know some people in the room know of hybrid automata, but does everybody? Not everyone. No? All right, good.
So the question is, do we know or do we not know?
Well, either way, I guess. How many people know about hybrid automata? Okay, so most people, all right, I guess. But okay, so I'll go through this quickly. So this is one of our canonical examples. So we have different modes like you would have in a state machine. In these different modes, additionally, we have associated differential equations that describe the evolution over intervals of real time of some set of real valued variables associated with the model. So this is the syntax, and then I'm kind of giving a picture of what the semantics would look like. So this is an execution or a run of this system. So the transitions can occur non-deterministically. So the transition in this case from off to on, may occur at that point where the temperature goes below T on, and then according to this invariant condition, it must occur at that time when X may be becoming less than T min, right? So the trajectories we would see is something like this. And we'd have similar behavior when we're back in on. Right, any questions on this? Good for everyone? All right. So executions, which is what we talked about on the previous slide, is a sequence of states and actions starting from some initial states. So it's a sequence mathematically. For models such as hybrid automata, we have this extra detail that some of these pieces would actually be curves, intervals, for the continuous trajectories. Okay. So for one of these types of models, and for these sequences described in the behaviors of the system, like executions, we can define a few things, such as what it means for a state to be reachable. So a state would be reachable if there exists finite execution starting from an initial state and ending in that state. So you can then talk about the set of all those states. So what is the set of reachable states? It would be all states you can get to by following behaviors of the system, starting from an initial state. We can then talk about invariants, things like, typically that would be modeling things like safety properties with. So some predicate over the state space would be an invariant of that system model if every reachable state satisfies this. So let's talk about that with another picture. So these are some abstract executions in a state space. If I consider the set of all states we can get to by following those executions, that would be some set in the state space, this reach A, and then some predicate over the state space P would be in an invariant if the set of reachable states is contained in it. Good. All right, so what does this mean? Well, if the set of reachable states, that's everywhere we can get to from an initial condition by following whatever is described by our system model. So if we consider all the places we can get to, then if we're contained in some predicate P over the state space, then that must hold, because we can't get anywhere else. So essentially we're saying there's no execution that could take us outside of this set reach of A, in this case that's contained in P. So since there can't exist this red trajectory, we would therefore know that P holds. Good on this? Questions? Right. Okay, so then how can we use this to perform verification? So you can perform verification if we can compute this set, reach of A, and then check a few other things, such as we need to be able to compute this set of reachable states, and then we also need to be able to computationally perform this check that the set of reachable states is contained in some property or predicate over the state space P. So you can also consider this in a dual version where instead of thinking of P as something good, you think of the negation of P as something bad. So forward reachability analysis would start from this set of initial states, and symbolically we'll compute frontiers. So how do we represent that? And then if we're representing the set of bad states as the negation of what we want to be invariant, we then, instead of checking that subset relation between reach of A and P, we could check the relationship between the intersection of reach of A and not P. So if that's empty, then it's equivalent to that subset check. So you can do this in a backwards way as well, but I'll skip that. So when would we know that we're finished? So that's sort of abstractly how we'll do this, and I'll talk a little bit more about practically how we can do that and some of the methods for doing that. And I'll talk in more detail about some of the methods for that in the later lectures, particularly how can we do that at runtime and with real-time guarantees. So as a part of this, when would we know that we're done, right? So when would we know we've computed that entire set of reachable states? So if we reach a fixed point, so if that computation can reach a fixed point, then we're done. So we can generalize that and actually say that if we have a new set of states that we're computing in any way we could get to at a next step I+1 from some representation of that set of reachable states at step I, then we're done. So the intuition behind this would be that there are no new states reached, so we can stop. So there's some assumptions that would go in here, like this essentially being a breadth first type of a search. So we would explore every transition that's possible at iteration I. Right, so there's some nice relationships between this and other areas and equilibria and control theory, probably in game theory, which I know nothing about, so it's good we have expertise here. All right, so how can we do this then? So we're going to start from our set of initial states and try to compute this, and then show that we don't intersect with these unsafe states. So one of the challenges for these types of models that we work on is accuracy. So it will turn out that we cannot exactly compute the set of reachable states for most interesting systems. So for instance, even for linear differential equations, we can't do this exactly. So we resort to over-approximations. So then how precisely we can perform this computation becomes important. So an over-approximation of the reachable states would be something we're doing in the computation. So we'd have a guarantee when we develop algorithms to perform that computation that it really does contain all of the reachable states. But how close we get's important, because essentially all of this region between the actual reachable states and this approximated or over-approximated reachable states, this is in essence error, right? So if one of these gray states intersect with the unsafe states but not with our yellow set, that means it's spurious. It couldn't have actually happened in the real system, but because of our approximation it could. So making sure that this is reasonably accurate to be useful is something that'll become important for these types of methods. All right, other questions? Good. Okay, so one of the, yes?
Just a small question. Earlier on the slide you said that even for linear systems, every set can't be computed exactly. Can you say a little more about that?
Yeah, so there's some special cases, but in general you can't symbolically compute it. So it's undecidable, right? So you can approximate it in a sound way, but you can't do anything better than that. So there's some special cases, for example, so one of the intuitions, right, is that the solutions of linear differential equations are exponential terms, right? They have sinusoids and these transcendental functions. So the solutions of these are the matrix exponential, and I can write it out. Does everybody know what I'm talking about? Or maybe to write? Okay, all right. But that's kind of the intuition. Now there's a special case where those solutions could be polynomial for linear systems, and in that special case, then you can maybe do a bit better. Oh. That good? Other questions? Yeah, I mean, even for simpler dynamics, right, the barrier between initialized rectangular hybrid automata and rectangular hybrid automata, so whether you have resets on transitions or not. Other questions? Yeah.
One more question. You always assume that you perfectly know the model of the system, correct? That you know the function f that predicts the reachable states.
No, yeah, so that's an excellent question. And this comes back to the core of the model validity question, right? So are the models reasonable representations of the physical world? So most of the formalisms do support non-determinism in the continuous aspect of the system as well. So we have these discrete transitions, right, that could be non-deterministic. So transition may or must occur. So instead of it just being a pure differential equation, you often can think of it as a differential inclusion. So it's a set valued thing. So the continuous part is actually set valued. So if you do that, you can then incorporate non-determinism, say, in parameters, right? So I think I have a slide later that I don't know if I'm going to talk about today or not. But as a concrete example, if you think of a circuit, an analog circuit where you have resistors, capacitors, inductors, each of those things, you never know those values perfectly, right? You know them with some tolerance. So you can incorporate that type of uncertainty into the models. So you get this kind of set value differential equation instead of just differential inclusion, instead of just an exact differential equation. Yes. So you can then incorporate in the reachability analysis as well. And it's pretty natural to do because you're already manipulating sets of things. So as you'd be doing these computations iteratively.
But it doesn't include external disturbances if you look at control systems, for example.
So again, you can incorporate these things. And the typical modeling way that this would be done is as some additive noise. So most of what exists right now, there are some results on stochastic hybrid systems where you may have more precisely characterize the noise or something, like whether it's has some Gaussian distribution or whatever. But in a purely non-deterministic way, you can model disturbances as well, just by often an additive input, right, that's set valued. So again, you get a differential inclusion instead of a differential equation. And it's pretty much it's the same reason as why you can have set valued parameters. That makes sense. But this is all going to be very worst case because you're not typically, I don't know of many tools at this point that would incorporate the distributional aspects. I think there's a couple maybe, but it's not the standard practice.
Thank you.
Yep. Other questions? Yeah, but I think that's an important point. So it's actually a potential criticism of this whole 5 minutes. Okay. It's a whole potential criticism of the whole hybrid systems area. It's actually not clear what the impact of the area has been, in my opinion. It's a beautiful conceptual modeling formalism, but it's not like model checking of digital logic. We don't have the impact of that, where every semiconductor company uses model checking in the design of circuits, right? We're nowhere near that. And I think in part, CPS is nice, but for us to really have impact in CPS, it's just too hard, because you have to solve software verification in addition to all this hybrid verification, and it's just... So my view is the potential impact that the whole area really could have is in analog mixed signal circuitry. But only so much work in that. CPS is great as motivation, but it's just sort of very hard. Okay, so how can we do this? I'll give the intuition of that, and then I'll give an overview, just very briefly, of what I'll talk about the next couple of days. So how can we do this? Set computations. So we'll alternate doing analysis of the continuous evolution and the discrete evolution. So we do this with a post-computation. So if we, say, start with this temperature and we're in the mode on, where we're increasing the temperature, we compute this post, we see where we could get to. Well, the maximum value we could get to would be Tmax. So we take that. We then may have to take some intersections, in particular with this guard condition of where we could make this transition, and that maximum value of where our temperature could have gotten. Then from that, we would use this as a new initial set of states to compute, again, a post computation in the next mode. And then we go back and forth like this. So at the end, we can associate which discrete state we're in with what the values of the temperature would be. But this would be about what we would get at the end. Okay, so our temperature can be between Tmin and Tmax. Modulo the first initial part, so a little bit beyond that. All right, so most of the methods are going to focus on this type of computation, whether there are, how you're accommodating for real time. Some methods you can think of accommodating for real time just like you would in a simulation of an ODE, so you're propagating forward in time these values. Then there are some other types of methods that may not necessarily have to keep that precise of track for it. So we have some tools for this, but I'll skip that in the interest of time and maybe talk about it in one of the next one, unless people want to know some of the tools. No, okay. So what are we going to do for autonomous stuff? So quick overview. So if we think about an autonomous system, in this case, just suppose I have a ship, but it doesn't really matter, some system. We have some environment, and we could have different architectures for an autonomous CPS. So these LECs are learning-enabled components, maybe that have been trained in a data-driven way. So we might have some perception learning-enabled components. Maybe we have some control learning-enabled components that are doing some adaptive control. And this could be the type of architecture that we have. So perception is either doing vision or combining vision with radar, LiDAR, other things. So that would allow us to do things like identify obstacles, what size, shape they are, if they're moving, etc. We might have disturbances coming in from the environment that are going to affect our control, such as wind. But at the end, we still want to control our physical plant to do something. We may also have some disturbances coming in. In the case of the ship type of example, you could imagine waves and other things. So there are other ways that the type of architecture could be designed. So this is in a kind of componentized manner, whereas in this one we have an end-to-end learning-enabled component. This is, as far as I understand, kind of what NVIDIA's done, like learning to drive from video. There are some strong V&V aspects of why this is probably not a good idea. I mean, how are we going to make sense of what's going on in there? We'd have this kind of monolithic thing we need to analyze, whereas if it's componentized, we may be able to individually analyze all those components to try to characterize their behavior. All right. So let me skip forward to kind of a summary slide that I have. Within the remaining 2 times, I'm going to talk about design time methods, which is going to be analysis of neural networks and doing things like reachability for neural networks. And then the other one will be doing runtime and online verification for systems that incorporate learning-enabled components within CPS. So we'll do that with some reachability analysis at runtime. All right, but that kind of gives the introduction to some of these type of methods within CPS and modeling formalisms like hybrid automata. So then I'll talk about how we can model neural nets, at least certain classes of neural nets. So many neural nets, you can just think of them as a function, right? So a feed-forward neural network, what does it do? It takes something from some input space and it produces something in some output space. So a formal model of that is as a function, right? So the modeling of that's pretty simple. Whereas if we have modes and things, the hybrid automata modeling is a little bit more complicated than just a function. Now, if you have other types of neural nets like recurrent nets, which may have state, that modeling is going to get a bit trickier. But anyway, so we'll see some more details of that. So thank you for listening. If there are any questions.
Thank you very much, Tyler. Any questions from the audience? I have a quick question. Can
Sure.
we see the slide on tools?
Oh, sure. So this has some of it. Yes. So this is a tool that we have called Hist that, on the one hand, the whole idea of it's actually quite stupid.
It's just the jet lag talking.
Yeah. Maybe a little bit, but no, it's unfortunate we needed to do this. But the hybrid systems community got into this unfortunate scenario where we had all of these different methods which internally supported, and I'm going to use the word roughly the same semantics. So everything supported roughly hybrid automata, maybe some minor differences. However, they all had different input syntaxes. So you have something with the same semantics, but just with a different input syntax. It's sort of very silly. So that's the silly part of what Hist does, is it does translations from a format that's generally quite good and supports things like networks of automata and a bunch of advanced features where the semantics issues do become tricky and you have to carefully think about, but to a bunch of the other state-of-the-art tools. So these are all model checkers for hybrid systems. This is Simulink and Stateflow. So there's also some methods incorporated to translate from hybrid automaton models to Simulink Stateflow models, which probably most people are familiar with, but this is part of MATLAB and is very commonly used in many industries for designing CPS. Yeah.
It's a silly question. So you mentioned hybrid systems are like a good way of modeling, right? Like they're very powerful, but they haven't really made that impact like when it comes to like CPS.
That's my view.
Yeah, can you elaborate on that a little bit? And then why do we have any hope that they would like make an impact and like using them for neural networks? Like you'll talk about that next time, I guess. But like, what is special about CPS that makes it hard to use? Like,
yeah. So the core thing, I think. So I mean, in the neural network world, at least with feed-forward nets, the modeling of that is actually really simple. So it's not that much more to add in to the hybrid automaton type of formalism to support that, because it's just a function, right? Now, if it's a recurrent net and it has internal state, then it gets more complicated.
But isn't CPS also, you can think of that just as a function, like?
Well, it has internal state though, right? So that's one of the things that makes it complicated. So my view, the whole hybrid systems area, I mean, I work in the area, it's sort of a, yes. No, within CPS, really the view is you have to solve the software verification problem, right? So I mean, in my motivation, what did I talk about? Like complexity growth of software. But then I'm modeling things as like, finite state automata, basically. Right, so I think you have to solve the software verification problem within CPS, plus a whole host of other issues, like modeling networking. Because there's lots of issues with, say, if you're using wireless communications, which I think some speakers are going to talk about, with message drops, delays, all sorts of things. So, whereas if you look at where formal methods and model checking have really been successful, it's in the more, it's been making a lot of inroads in software verification recently, but historically the big impact has been in the semiconductor industry. I mean, literally every chip, they're buying tools from Synopsys and Cadence that are built on equivalence checking or model checking. And that type of impact is not clear at all in the hybrid systems area. Within tools like Simulink Stateflow, there is a capability to model systems as hybrid systems, but there's not as a modeling concept. That's the impact so far. It's not like any of the verification methods are actually, really being applied in practice. And I think it's within CPS, I really think the issue is the software side. And then model validation, I mean, the plant validation comes up with what the question was. That's a big challenge. And I don't know. I mean, I think some of it's maybe historical. We want this philosophical thing that really produces proofs. But
Yeah.
what we can actually do proofs about is very different than the systems we're actually talking about, right? Nowhere in here do I see any source code, right? It's sort of, then I'm using motivation of a modern aircraft has 25 million lines of source code.
So can I chime in here?
Sure.
So I think that it's good to be a little bit more patient with reachability analysis and hybrid systems reachability analysis, because in a way, Tyler mentioned model checking of digital components. Well, that would be part of a hybrid systems reachability analysis. You'd have to do that as part of a complete reachability analysis. So hybrid systems combines all of the digital and all of the continuous, and that's a lot. When somebody was asking Edward Lee a few years ago what is exciting about CPS, he said, well, basically, we have all this continuous math that has developed for a few hundred years and all this discrete math, and now we want them to come together, and that's tough. So we have these foundational challenges for hybrid systems, but also, when you've solved reachability or verification of hybrid systems, you basically have, that requires solving all the other problems as well. And the focus on reachability of hybrid systems or dealing with hybrid systems is much more recent than trying to verify digital systems or prove properties. Tony Hoare was talking about proving properties of programs in the 60s, and the papers by Allure and Hensinger on hybrid systems are from the 90s. So you can give at least 30 years to hybrid systems to catch up. So I think that it's
No, I mean, I work in the area.
Yeah,
It's a good area, but I mean, we can work on it forever. It's great. I don't think we'll ever solve all the problems.
Yeah.
It's a nice area to work in. No, and I agree. And I think the issue with CPS and hybrid modeling, part of it is really the software verification problem. Because for normal non-control software, that problem is not solved, right? That's an ongoing problem. A lot of interesting results and automated analyses and things for software model checking, but that's not, I think, by any means a solved problem. And I don't think for circuits we're totally solved. But I think the big potential nearer term impact that the whole hybrid systems area can have is on analog mixed signal circuits, because the modeling formalism is more close to the behaviors you'd see in those types of systems, right? You throw the software problem mostly out the window. You could talk about the software in terms of discrete mode changes and things in a reasonable way. Whereas if I'm implementing a neural net in whatever language, I mean, it's okay. All right.
Any more questions? Very good.
Okay.
Thank you
All right.
very much, Tyler.
Thank you.